everybody, I wanted you to go ahead and get a review of chromatography techniques that we've talked about in Chem 4375. Specifically, we talked about 3 different columns, and I addressed them a little bit at the end of the last presentation, but I want to go ahead and talk about it a little bit further today. So we'll go ahead and get started. Right here, the first thing that I want to talk about is ion exchange chromatography. Now, anytime that you talk about ion exchange chromatography, what you need to understand is actually column chromatographies. The 3 types that we'll talk about today or in this video are all fairly similar to one another. They're all based upon a column that has a resin or a collection of beads within them. Now, I'll just go ahead and expand this out. The beads that we're talking about are generally something like, they could be something like cellulose. They're going to be an insoluble and inert molecule. They're going to be an insoluble sugar or something like that. And a modification is done to those beads. So one of the things that I always like to think about is what's a molecule that we've talked about in class and that molecule has a charge to it. Well, one example that you could think about at a physiological pH would be CH2, CO, O-. Now, if you recall your amino acid structures, which you most definitely should, this should resemble the R group of the amino acid, aspartic acid. So, aspartic acid. Now, I know that I never asked you to know the pKa's of the different R groups. However, this being an acidic group, you should know that the pKa is fairly close to, it's going to be a fairly acidic one, so this is about 3.5 or so. So at a physiological pH, you are going to indeed have a group that has a negative charge. Now, what is that going to be attracted to, or what will that attract? That will attract positively charged molecules. Now, whenever we talk about column chromatography and ion exchange chromatography in a biochemistry class, generally you are talking about purifying a protein, so purifying a positively charged protein. But it is important to recognize that we do need to talk about, well, any molecule with a positive charge, this group will attract, okay? But with that said, generally we're going to be talking about positively charged proteins. So whenever you see a group a bead that has a negative charge to it, what is that going to attract? That's going to attract cations. Now, with those cations, that is the way that we're going to use the molecule that we would aim to attract to describe or to further define this type of column chromatography. So this would be known as, if we had a negatively charged group permanently affixed to the bead, this would be cation exchange chromatography. So this is known as cation exchange chromatography. So the terminology comes from what is the molecule that you are trying to attract? What is the molecule that you are trying to bind? We are trying to bind a positively charged protein. So that positively charged protein, that is our cation. And so what we are going to use more or less as our bait is a negatively charged R group. So we make a modification to the cellulose bead. What we decided to affix to it was the R group for an aspartic acid like aspartic acid, or R group for an amino acid like aspartic acid, sorry about that. And that negatively charged molecule will attract cations. Okay, so with that said, in the event that you put a positively charged group on the cellulose bead, if you put a positively charged group, so let's just do R+. So arginine, for example. If you've permanently affixed the arginine R group to a cellulose bead, and you're trying to do ion exchange chromatography, what is that going to attract? That's going to attract negatively charged proteins. So that would be referred to as anion exchange chromatography. And I'm going to go ahead and write that. So that would be known as anion exchange chromatography. And that's an important distinction and an important thing to acknowledge about the differences between these two different types of ion exchange chromatography. So it is not, the terminology cation versus anion exchange chromatography does not come from what you permanently modify the cellulose beads to have, but instead, what is your target? What are you trying to bind? Okay, so make sure that you keep that straight and you will be in good shape. Now our next type of chromatography is known as gel filtration chromatography. Now gel filtration chromatography is a type of chromatography in which you are going to purify proteins based on molecular weight. Separation by molecular weight. And the way that gel filtration chromatography works is, again, you're using these small beads, but the difference is that these small beads, I always try to think about them as having little grooves and crevices within them. So here's an example bead that has 2 pores within it. Now, let's go ahead and draw 2 different proteins. One is a blue protein, and one is a significantly smaller orange protein. Now, imagine that you have tons and tons of these beads, tons and tons of these small spherical beads with 2 major pores within them. Now, if you look at this blue bead, one of the things that you'll notice about it is, will it actually fit into that bead? Now, I understand we're looking at something on 2 dimensions, on an X and Y axis, but just imagine that this bead is just too small for this large protein to fit in there. And so what is going to happen is that bead is basically going to see this opening, and it's going to migrate quite quickly past it. On the other hand, we have our small bead, this orange bead. What is that going to do? That's going to enter the pores. That's going to enter the pores within this column, and what's going to happen to it is it's going to basically get stuck. Now, it's not going to get stuck permanently. However, it is going to get stuck for, a considerable amount of time. And when it gets stuck, its ability to migrate through these pores is delayed quite a bit. Will it make its way through? Absolutely. But it's going to go through it at a much slower rate. And so globally, it's going to migrate through this entire column much slower than our blue bead. So one thing that we could do is basically we could collect individual fractions. So collect 1 milliliter at a time. 1, 2, 3, 4, 5, 6. Okay, so let's imagine that this is our first, second, third, fourth, fifth, sixth. Our 6 fractions that come off of our column. Now the first protein that is going to elute off this column is going to be our blue protein. So that would be collected in our very first fraction. So this one, you could relate a size to it. You could say that, well, this one's 120 kilodaltons. So we can look at these proteins, and this is a very simple example. We're not working with a complex mixture. In this example, we're looking at just 2 proteins, and let's say that the blue protein is 200 kilodaltons. So 200 kilodaltons, and our orange protein, let's say that's 45 kilodaltons. Well, we will see a relationship between when these proteins elute from the column. So here's our 200 kilodalton protein. That's our first one to elute. Now the last one to elute of our 2 proteins is going to be our orange protein, checking in at merely 45 kilodaltons. And the reason for that is because the blue protein goes through the column as fast as possible because it has no reason to stay there. Whereas our orange protein has a little bit of a reason to stay there because every single bead that it encounters, it's going to migrate through at a very slow rate. So that's ultimately what you're going to see with gel filtration chromatography. Now, the way that you will visualize gel filtration chromatography quite often is by using something known as a chromatogram. And a chromatogram is a plot where on the y-axis you're going to look at the absorbance at a wavelength like A280. So A280 is a great way to measure whether or not you have protein in your sample because at 280 nanometers, proteins with aromatic residues are going to absorb light. Now, if we use, so that's our y-axis. On our x-axis, well, we have our fractions. So fraction 1, 2, 3, 4, 5, 6. Okay, so we had a total of 2 proteins. So we would see a large peak in fraction number 1, nothing, nothing, nothing until fraction number 6, where we see our other protein. So again, this was an example that was very simple due to the fact that we were only working with 2 proteins here. But ultimately, that's the principle of gel filtration chromatography. So make sure that you are familiar with that. Now, our third and final type of chromatography is affinity chromatography. And generally, affinity chromatography is the type of chromatography that people like because it's the type of chromatography that people like because it's kind of easy to understand. So affinity. Now in affinity chromatography, what you are doing is you're exploiting a protein's ability to bind a specific compound. So if we took a protein like hexokinase, hexokinase is a protein that binds onto a number of different hexoses, but it's commonly known in the process of glycolysis for binding glycolysis. Sorry about that. That should be there. Glycolysis, and this is the process of breaking down sugars. So it will bind onto glucose. Now, hexokinase has an affinity for glucose. So has an affinity for glucose. Affinity. Now, not every protein has the same affinity for glucose. If you think about something like hemoglobin, hemoglobin has a high affinity for O2, but not much for glucose. And so if you are working with hemoglobin and glucose as an example of 2 different proteins, if we were working with hemoglobin and hexokinase, it would be good to use a technique like affinity chromatography. In affinity chromatography, what you're going to do is you're again starting with something like a cellulose bead. And to it, what you are doing is you are going to put a molecule like glucose. Okay. So whenever hexokinase, which will indicate as a blue protein, and then let's go with hemoglobin as our red protein there. Now hemoglobin, when it sees glucose, it will say, oh, how about that? And continue straight past the bead that has been modified to have glucose. Hexokinase, on the other hand, what it's going to do is see, oh, well, this is something that I natively have an interest in. I have a high affinity for this. I prefer to bind to this molecule and phosphorylate it. And so hexokinase is going to stay there. So if you are working with 2 simple proteins like hemoglobin and hexokinase, affinity chromatography would be a great technique because you are going to be selecting for proteins with a specific interest or specific affinity for a substrate. Now, a question becomes, how do you elute a protein from an affinity chromatography column? And, well, it's also kind of easy. Add free glucose. So whatever you've used to basically immobilize, or whatever you have permanently modified the beads to have, for instance, glucose, your protein hexokinase has a great affinity for that. Now, you know that hexokinase has that affinity, so what you're going to do to elute the protein is just add more of that molecule, but make it a molecule that's free and is not immobilized. So glucose is, you're just going to flow a glucose solution over that column, because hexokinase slowly but surely will have a greater affinity for the glucose that's freely available in the solution over that which is permanently affixed to the beads. So ultimately, there are three major techniques or major types of chromatography columns. They're all built upon a similar foundation of those insoluble sugar beads. You just make modifications to them. In the example of affinity chromatography, you're going to make a modification and add a molecule to that. In the case of gel filtration chromatography, there are small pores or crevices that small proteins will fit into, large proteins will not fit into those. Those large proteins will just go straight through the column. Then with ion exchange chromatography, know what you are trying to bind to. So you are trying to bind a positively charged protein, thus you are doing cation exchange chromatography. Alternatively, you are trying to bind a negatively charged protein. You're trying to purify a negatively charged protein. Therefore, you are doing anion exchange chromatography. Anyway, I hope this helps. I hope this illustrates these three different chromatographic techniques well. Thank you very much for watching. Have a good one.